Okay, you've got that big interview coming up, the one for a data engineering manager, and you know the pressure's on, right?
Definitely.
Not just talking about managing the team, but really showing you understand the technical how and, well, the why behind the systems you'd oversee.
Yeah, that technical depth is key for a manager role.
That's exactly what this deep dive is for. We've sifted through all that material you share, the articles, the notes, and pulled out the key technical bits, the concepts you really need to, nail those technical conversations in the interview.
Right. Our mission here is to unpack the essential tech, the architectural ideas, and the critical things the material highlighted as vital for a data engineering manager.
The goal.
So you feel totally confident talking about the tech landscape and the role's impact, drawing straight from what you've already studied.
Okay, let's jump right in then. First things first. Based on the material you send over, what is a data engineer? Like at their core?
Well, the sources frame them as kind of the architects of the digital age. Fundamentally, they're creating and maintaining the data architecture.
The foundation.
Exactly, and building those, critical data pipelines.
So it's more than just pushing data around. It's about the actual design and infrastructure.
Precisely. A core job highlighted is turning raw, often messy data into something genuinely useful. Meaningful insights.
Which means building pipelines, sure, but also
constantly tweaking them, streamlining them, and really focusing on maintaining data quality all the way through. That came up a lot.
And why are they seen as so crucial right now? What does the sources say?
It really boils down to businesses being so data-driven now. I mean, they rely on data for strategy, for innovation, for just staying competitive.
So engineers build the plumbing for all that.
To build the foundation, yeah. Without them, none of that data-driven stuff really happens effectively.
That strategic piece really stood out. And the demand for them reflects that, right?
Oh, absolutely. There was that Gartner report mentioned, projecting, what was it, a 90% increase in demand by 2025.
Wow, 90%. That's huge.
It is. And it ties directly back to, businesses needing more data, more automation, fueling AI, all that.
So from a manager's perspective, thinking about that interview, what are the key responsibilities beyond just pipeline building?
For a manager, the sources really underscore ensuring data integrity and security. Those aren't just tasks, they're like architectural pillars.
Got it.
They also point to optimizing systems for scale, knowing data volumes just keep growing, and maybe most importantly for a manager, collaboration.
Working with other teams.
Exactly. Data scientists, analysts, IT, making sure data flows smoothly and everyone who needs it can get it.
Okay, so understanding the tech and how it serves the rest of the business. Makes sense. All right, here's where we get into the real technical meat for that interview prep. What are those essential pillars you absolutely need to discuss? Let's start at the base. Databases and storage.
Okay, so the material made a really clear distinction between two main types. OLTP, online transaction processing, and OLAP, online analytical processing.
And the core difference in purpose that a manager needs to get.
Right. OLTP systems are built for transactions. Think high-frequency stuff like inserts, updates, deletes. The example in your source was processing live orders on an e-commerce site. It's about handling individual things fast and reliably. OLTP systems, though, they're designed for analysis. They use column-based storage usually, and they're great for complex queries, summing things up, looking at historical data. That's your BI reports, trend analysis stuff.
So OLTP for the now, OLAP for the looking back and figuring things out.
You got it. And a really key point the sources made is that data often needs a lot of transformation moving between them, from that fast transactional OLTP structure to the analysis-ready OLAP structure.
Okay. And beyond those traditional relational ones, NoSQL came up too. What's the big idea there?
Yeah, NoSQL, so non-relational. The key things are flexible schemas. They don't have rigid structures like relational tables, and they're designed for horizontal scalability.
Meaning you can just add more servers to handle more load.
Exactly. But there's a trade-off, and the sources highlighted this. They often relax those strict ACD guarantees. Atomicity, consistency, isolation, durability.
In favor of what?
Performance, usually, and something called eventual consistency. It's okay if things aren't perfectly synced immediately everywhere as long as they get there eventually.
And where would a manager think about using NoSQL based on the reading?
The use cases mentioned were often about rapidly changing data or huge volumes, where that flexibility and scale are more important than strict consistency. Think user session management, performance monitoring data, social media feeds, IoT data, stuff like that.
Makes sense.
The material also briefly touched on the different types: key value, document, graph, column-oriented, multi-model. Each has its own strength, depending on how the data is shaped and how you need to access it.
And alongside these, the difference between data warehouses and data lakes. How did the sources position those?
Right. So a data warehouse was described as typically very structured. Data's already cleaned, transformed, optimized for BI tools and standard reporting.
Near polished.
Yeah, exactly. A data lake, on the other hand, is more about storing raw data, structured, unstructured, semi-structured, whatever, at scale. It gives analysts and data scientists flexibility to explore data before it's forced into a specific structure.
So it's a choice based on who needs the data and how processed it needs to be up front.
Pretty much. A key managerial decision point there.
Okay, that maps out where data lives.
Hmm.
But interacting with it, SQL is obviously huge.
Oh, fundamental. SQL is presented as the standard for relational databases. And for the interview, you definitely need to be comfy discussing key operations and, maybe more importantly, the implications of choosing one method over another.
Like joining tables. That seemed basic but important.
Joins are critical. The sources specifically called out inner join and left join, the key difference being how they handle rows that don't have a match in the other table.
Which impacts the results significantly.
Hugely. It's not just syntax. It's about making sure you pull the right data. That's data integrity, which is vital.
Aliases also popped up. Simple, but why mention them?
Aliases, using AS or just a space, yeah. They seem small, but they make complex queries way more readable, especially with multiple joins or subqueries. A good manager appreciates code that the team can actually maintain.
Good point. What about combining results, union versus union all?
Yeah, the material flagged the difference. Union automatically removes duplicate rows from the combined result. Union all keeps everything, duplicates included.
So the choice depends on
whether you actually need to count or see those duplicates for your analysis report. Purely a requirements thing.
And subqueries, they seem pretty powerful in the examples.
Subqueries are really useful for breaking down complex logic. Your sources showed using them in the select part to grab related info, or with the IN operator to filter based on another query's results, like finding all movies an actor was in.
Right.
But a critical takeaway the material stressed was that the order of operations in a SQL query really matters. It affects the result, obviously, but also performance. And performance is definitely a manager's concern when optimizing data access.
Okay. Moving beyond structured queries, how do you tackle the sheer scale and speed of big data and streaming?
Right. This brings us to frameworks like Apache Spark and Hadoop. Hadoop is kind of the classic for distributed storage, HDFS, and batch processing. Spark is known more for its speed, especially its in-memory processing.
I'd say good for it.
Faster analytics, iterative machine learning algorithms on big data sets, that sort of thing.
And the processing models themselves, batch versus stream.
That's a core distinction.
Yeah.
Batch processing handles data in big chunks, maybe overnight or every few hours. Stream processing deals with data continuously as it arrives, almost in real time.
And the choice is driven by
business need. Do you need daily summaries or do you need instant alerts? For those real-time needs, Apache Kafka came up as a major player, a distributed streaming platform, basically a message bus for real-time data. And Apache Flink was mentioned as a powerful engine for processing those streams.
use cases.
Things like real-time monitoring dashboards or detecting credit card fraud the moment it happens, that kind of immediacy.
That's a pretty powerful toolkit. Shifting gears slightly, data modeling also seems absolutely fundamental for building anything reliable.
Oh, essential. Data modeling is basically the blueprint for your database. It's how you formally map out the data structures and, crucially, the relationships between them. It brings clarity and consistency.
What's the go-to model for relational databases mentioned in the sources?
The entity relationship model, or ER model, that's standard. It's about identifying entities like customers or products, the relationships between them like customer places order, and the attributes of both like customer name or order date.
And the output is usually
Often a visual ER diagram, which is great for understanding, plus a detailed data document or dictionary. Both are super important for team communication and documentation, something a manager definitely cares about.
And within relational modeling, normalization is key, right?
Yes, normalization. The sources explain it as a technique to basically reduce redundancy and improve data integrity by breaking down tables into smaller, more related units.
The goal being
Often to reach third normal form, or 3NF. That means all the non-key details in a table depend only on the table's main identifier, the primary key, not on other non-key details. The sources mentioned 1NF and 2NF as steps along the way. Understanding this helps a manager design databases that are just easier and safer to update.
Okay, that's for relational. What about modeling for analytical systems, like those data warehouses we mentioned?
Right, for warehouses, dimensional modeling is the common approach. It's different. It uses fact tables, which hold the numbers, the measures like sales amount, quantity sold.
Metric.
Exactly. And dimension tables, which provide the context for those facts: who, what, when, where. Think product details, customer info, dates.
And there's specific ways to structure those.
Yeah, the two main ones discussed were star schema and snowflake schema. They're ways to organize those fact and dimension tables.
Difference being.
Star schema is simpler. Dimensions connect directly to the fact table, but might have some redundancy in the dimensions. Snowflake schema normalizes the dimensions further, breaking them down, which reduces redundancy but means more joins are needed for queries.
So a trade-off again.
Always a trade-off. Simplicity versus normalization, query performance versus storage. A manager needs to weigh those based on how the warehouse will be used.
How do you handle dimension data that changes, like a customer moves or a product category gets updated?
Ah, yes. Slowly changing dimensions, or SCDs. That's a classic data warehousing challenge. The sources detailed 3 main types you should definitely know for an interview.
Okay, type 1.
Type 1. Just overwrite the old value. Simple, but you lose all history of the change. Type 2. This is really common. You add a new row in the dimension table for the change, keeping the old row but marking it as inactive or using date ranges. You preserve the full history.
In type 3.
Type 3. You add specific columns to the dimension table to hold both the current value and the previous value. Gives you limited history directly in the row.
So choosing the right SCD type comes down to business needs again. How much history do you actually need?
Exactly. It's a direct requirement driven by the kind of analysis people need to do, a key decision for the manager to guide.
Okay, structure's covered. Now, how does all this data actually move through the system? That's pipelines, right?
Yeah, so all this modeling and storage design, what does it mean for actually getting data from A to B? That's where data pipelines come in. Fundamentally, it's a series of automated steps.
Processing.
Right. Processes designed to move data reliably from a source system to some destination usually involves extracting it, transforming it somehow, and then loading it. The core parts, as you mentioned, are the data sources, the processing units where the transformations or quality checks happen, and the storage systems where the finished data lands.
And we always hear ETL versus ELT. What's the key difference the sources pointed out, and why choose one over the other?
Okay, ETL, extract, transform, load. You pull the data, transform it before it hits the destination, often using a separate engine. ELT is extract, load, transform. Pull the data, load it straight into the destination, maybe a data lake or a modern warehouse, and then transform it using the power of that destination system.
And the choice depends on?
The sources suggested it often hinges on the destination's capabilities and how agile you need to be. ETL might be better for older systems or destinations that can't handle big transformations.
While
ELT is really common in modern cloud setups. You leverage the power of cloud warehouses like Snowflake or BigQuery to do the heavy lifting of transformation after loading. It can be more flexible. The sources even mention zero ETL as this emerging idea, using direct integrations to skip building traditional pipelines altogether sometimes.
Interesting. But just building the pipeline isn't enough, is it, with all those steps and dependencies?
No way. You need to manage the whole workflow. That's data orchestration. It's absolutely essential for coordinating complex jobs across different systems.
Making sure things run in the right order.
Exactly. Handling dependencies, job B can't start until job A finishes. Scheduling runs. And crucially, handling failures and retries automatically. Tools like Apache Airflow, Luigi, Prefect were mentioned as popular choices for defining and managing these workflows. For a manager, understanding orchestration is critical for building data platforms that are actually reliable, maintainable, and you can see what's going on observability.
So orchestration is like the conductor, making sure the whole data orchestra plays together smoothly and reliably.
That's a great analogy, yeah.
Okay, beyond the pipelines themselves, what about those critical things that cut across everything?
Yeah.
Quality, governance, security. The sources emphasize these for a manager. Right.
Hugely important. Data quality came up again and again. The point was simple. Data is only valuable if it's accurate and reliable. If people don't trust the data, the whole system is undermined.
What specific aspects or dimensions of quality did the material highlight?
It listed 6 key dimensions. Accuracy, is it correct? Completeness, is anything missing? Consistency, does it match across systems? Timeliness, is it available when needed? Validity, does it follow the rules? Like, is an email address actually an email address? And uniqueness, no unwanted duplicates.
And how do you maintain that?
Practices like data profiling, understanding your data, first setting up validation rules, and data cleansing processes were mentioned. Then there's data governance. This is broader money. The policies, processes, standards ensuring data is available, usable, has integrity, and is secure.
Making sure people can actually use the data properly.
Right. A practical aspect mentioned was making data discoverable. Can people find what they need? And understanding it. Clear column definitions, documentation, vital for a team.
And data security. Obviously a massive one, especially with sensitive data.
Non-negotiable. It was framed as a major non-functional requirement, something you have to build in from the start, not tack on later. The sources brought up the classic CIA triad.
Confidentiality, integrity, availability.
Exactly. Confidentiality, only authorized people see it. Integrity, it's accurate and hasn't been messed with. Availability, it's there when you need it. And for practical implementation, a manager needs to ensure things like the principle of least privilege, minimum necessary access, encryption both for data sitting still at rest and moving in transit, anonymizing PII, especially in logs or non-production environments, and using proper secret management for passwords and keys.
Right, not hard-coding secrets.
Please no. A key takeaway from the sources was that these security foundations should really be in place before you even start building major pipelines. Get the groundwork right first.
That proactive security stance makes total sense. Okay, let's round things out by looking at the wider ecosystem, the specific tools, languages, platforms the material brought up.
Sure. For programming languages, Python was definitely highlighted. Great for scripting, data wrangling with libraries like pandas, building tools. And SQL, as we said, is just essential for anything relational.
Any others?
Java and Scala got mentioned mainly because they're used under the hood in big data frameworks like Apache Spark. And the sources also suggested that just being comfortable with basic Linux commands is pretty useful for managing things.
Makes sense. And cloud computing. It's everywhere in data engineering now.
That's absolutely central. The sources talked about the big 3, AWS, GCP, Azure, and the service models.
Yeah.
You've got IaaS, infrastructure as a service.
Like raw virtual machines, basic storage.
Right, EC2 instances on AWS, that kind of thing.
Yeah.
Then PaaS, platform as a service, managed databases, managed Spark clusters where the cloud provider handles the underlying infrastructure for you. And SaaS, software as a service, which are fully managed tools.
And understanding these helps a manager.
Make those build versus buy decisions, manage costs effectively. The material also noted that while providers offer similar types of services, some tools might be tied to one cloud, while others, like Snowflake was the example given, can run across multiple clouds.
What about that term modern data stack? What do the sources mean by that?
Yeah, the modern data stack, it's less a single product, more an approach. It's about using spiralized, often cloud-native tools for each part of the data lifecycle and having them work together. Composability is the key word.
So best-of-breed tools for each job.
Kind of. The material gave examples. Tools for ingestion like Airbyte or Fivetran. For storage, platforms like Snowflake, BigQuery, Databricks. For transformation, dbt is huge right now, transforming data inside the warehouse. Orchestration tools like Airflow, quality tools like Great Expectations, metadata tools like DataHub.
Lots of tools.
Yeah, but for a manager, the key isn't just memorizing names, it's understanding why this modular approach is popular, the agility, the scalability, leveraging tools that are really good at one specific thing.
Got it. It's about the strategic fit, how they combine to solve the business problem.
Yeah.
Okay, so bringing this all together for that interview prep, we've really hit the key points from your materials.
Yeah.
Defining the data engineer role, its strategic value.
Mm-hmm. The core technical concepts databases, OLTP versus OLAP, NoSQL itself, big data, streaming, data modeling nuances like ERDs, normalization, dimensional models, SCDs.
Right. Then how data moves pipelines, ETL versus ELT, orchestration.
And those critical cross-cutting themes, quality, governance, security, the CIA triad.
And finally, the landscape of tools, languages, cloud platforms, and that modern data stack concept.
Yeah, this deep dive pulled out that foundational knowledge, the specific terms, the concepts straight from the sources you provided. It should really give you the confidence and the specific talking points for those technical interview rounds, demonstrating you get the landscape from a manager's viewpoint.
Because as that data engineering manager, you won't just need to know these things exist. You'll need to make choices, right? Choose the right tech, handle those trade-offs we talked about, build systems that are reliable, secure, and actually deliver business value.
Exactly.
So thinking about that leadership aspect as you head into the interview, maybe the final thought is, in this landscape that changes so fast, how do you balance exploring cool new technologies with ensuring the core platform you manage is stable, secure, and delivers practical impact for the business? That's a core tension for any tech manager today, isn't it?